So in this video, I'm going to be covering what are greedy algorithms and then how do we prove them. And honestly, like creating the greedy algorithm, it's not too bad, but honestly, like doing the proving part is like the beast of the problem because this can be kind of complicated to do. So just a quick overview. A greedy algorithm is something that is picking the best choice at a specific time without considering the future. So I kind of like to think about greedy algorithms as like a little toddler. I know like when you're a kid, you're very greedy, and so like you're probably going to like always pick eating candy and try to eat as much candy as possible because like at that certain moment, it probably seems like the best thing because you're gonna get a sugar rush and feel good. But the toddler isn't considering like the future, so probably in like 5 minutes later, they're gonna feel sick to their stomach. So that's like one example of a greedy algorithm that probably doesn't work, but to produce the optimal solution. So that's kind of example. Like sometimes our greedy decisions don't always produce like the optimal thing to do, but there are cases where they actually can, although those cases are honestly kind of few, but there's not very many of them, but they do exist, and when they do exist, we want to be able to show that they can produce an optimal solution. So that's really what we're doing in this video today. And so I also want to point out a really nice benefit about greedy algorithms is they're quite speedy, so a lot of times they'll be in polynomial time, whereas like some other types of programming algorithms like dynamic programming, which has to consider like all of our potential options, that's quite a bit slower than polynomial time. Okay, so how do we prove that the greedy algorithm that we've created will actually produce an optimal result? So we're going to use induction, very exciting. And so, of course, like all induction problems, we want to have an induction hypothesis. So for this, we will say like our O of k, which is just like an optimal solution where the first k choices of greedy are in O of k. So there's some optimal solution that exists where the first k choices that our greedy algorithm picked also occur in this solution. And a really common misconception is to think that there's only one optimal solution. A lot of times there can be multiple optimal solutions, but we're really only considering one specific instance. So if we write this out, the best way to think about this is as a set. So our greedy will pick a set of choices. So like say on day 1 I'm going to do something, day 2 I'm going to do something. And so whenever you're doing your proofs, you want to define what is a choice. Okay, yeah, define that. And then also, you need to define what does it mean to be optimal. So like, if I'm trying to figure out which days I should do certain homeworks to assign the most points, well, my k choices would be assigning days to homeworks, where the optimal would be like where I get the most number of points. So that's sort of how you should phrase your hypothesis. So yeah, if we're thinking about this as a set, our greedy solution will have some k choices, and we're defining a specific optimal solution for induction hypothesis where the first k greedy choices also happen to be in this optimal solution. So that's why we denote it by this O of k. And then they could be different. We don't really know what's going on here. And that's what we want to move on to. Okay, so for an induction step, we want to show that, you know, if we also include the k plus 1 greedy choice, that it can be extended to some optimal solution. So it means that like even if my greedy choice will like go on and will also make this decision, we want to show that like it's possible that like this subset will be in some sort of optimal solution. So case 1 is that g of k plus 1 is already an element in our optimal set. And so what would this look like? So this means like our optimal set would be like this. We already know our first, or like there are k choices that match with greedy. And we also know that somewhere our greedy's k plus 1 choice also exists in this subset, or in this set, sorry. And the really great thing about sets is like the order technically doesn't matter because sets are unordered data structures. So we don't have to do this, but to make things more clear, I can just rearrange our set to say that like you know, our first, sorry, I'm just kind of rearranging this order. And then this is good because it shows that our first k plus 1 choices are in optimal, or in a specific optimal solution. And this is kind of it. We can just kind of state that for our things. And I also just want to really reiterate, the optimal solution is just a given set to us. It's just a given solution set. We don't necessarily know, like, okay, they made this choice first, then they did this choice, then they did this choice. We don't know the order. It's just like, we just have the assignments, like day 1 equals homework something like 7. It's just a set of choices that have been made, not necessarily the order, because again, sets are unordered, so it doesn't matter. And I feel like that's a really common misconception because the way our greedy algorithm works is it is like quite sequential. But yeah, please don't apply that like same mindset for our optimal solution. Okay, the other case is that our k plus 1 is not an element in our like O of k. So this means we'd have to do something clever. Sometimes this can be called as like swapping, in order to show that our greedy choice, like k plus 1, still gives us an optimal solution. So even though this instance, might not contain g plus 1, we can show, for example, if we replace this choice with g of k plus 1, we need to show that this will still make an optimal solution. And there's a lot of ways to do this. Really the best way to do this is like do a lot of practice in order to understand. But yeah, this is just the general overview of how to prove greedy algorithms.